And also, Brian, can you make your announcement of what you would like people to do to fill out a certain form?
Yep. So at the end of Friday, this is just a reminder to fill out the survey of when to meet for office hours and help sessions at 7 o'clock tomorrow. I will send out what those office hours and help and the time of the help session, and I will start those next week. So just a reminder.
Thank you, Brian. So let me share screen just a moment. And I hope you guys can all see the screen now. All right, so we'll start in just another minute. All right, let's start. So I want to start where we left off yesterday or on Tuesday with a little bit more of a review of what exactly is going on. Then we're going to dive right into the details of packets 1 through 3 and also chapter 3, also chapters 1 and 2, although they're more or less review. So the basic idea that we contended with is that there are a lot of problems out there in manufacturing, relatively complicated, and they have a large number of parameters. So what we're going to do today is we're going to talk a little bit about the specifics of some more applications, and then we'll go into the packets. And you'll get an assignment, I believe, on Friday from Brian. Don't worry, it's not due for quite some time, but it'll help to know what's coming so that at least you can ascertain what is the most important thing to focus on, which will be primarily the optimization and robotics. So the main idea here is that, in the first example, we had this device from a vendor, the Sauertech 65. It was some giant large-scale 3D printer that did all kinds of crazy stuff. And it was just a motivator to indicate that whatever the parameters are in these kinds of models are not easy to control, and it's no point in trying to guess them. So we're going to take as our very first example the idea of a robot and how a robot prints up something as something we want to control. And that'll motivate a lot of what's coming later on in the class, which is how materials behave, how do they interact with heat, how do lasers interact with materials, how we use those in a manufacturing setting, and then all of the other things that follow along. So we'll do a little bit of material science in terms of the materials of mixtures, because that's of course central. Also the interaction of lasers with materials, and then of course stress and strain, how materials behave, what makes them last, what makes them fail. The primary interest is to set up something that's called a genomic or genetic string. The idea is that any physical system which has some merit is going to have many parameters. And so we're going to estimate those parameters by using a biological approach to get the best possible set that can deliver our response. Now this hinges upon the concept of what you see in the literature a lot these days, the so-called digital twin, which, as you can imagine, the phrase is a pretty good one. It simply means a digital replica of a physical system that has high enough fidelity that can be considered to be a duplicate of physical space. So the idea then is in the digital world, you can manipulate these models, you can test them out, you can test extreme events that would otherwise be dangerous in the laboratory or in the real world, and see first what exactly are the best possible scenarios. Then after that, you either build it or control it in the physical world. So there are lots of applications, as I motivated before. This doesn't have to necessarily land into just manufacturing. It could be firefighting with drones. It could be someone coughing in a crowded environment. So we're all concerned about that these days. Obviously, it could be decontamination instead of lasers, but it is the same kind of physical event where we have lasers or UV light that basically is trying to kill things onto the surface. It could be all kinds of other applications, and we'll get to those as time wears on in the semester. But our main focus here is that we have some kind of a computer model. We hope it's of high fidelity. It generates some simulation results, and we would like it to do something that's desired. We call that the desired results. We take the difference between simulation and desired and the appropriate norm. It delivers an error. We keep adjusting the parameters. And if the model has merit, if we find the correct parameters that match the desired results, then we go into the physical world and do something with that model. So the main idea is that every one of those physical systems has a key set of pieces of information, so-called DNA. For the robot, it might be the kinematics of it. It might be the grippers. Materials, it could be the various phases. Lasers, it could be beam intensity, duration. Solid processing, it could be heat applied, pressure, and so forth. And this could go on and on and on. And that's why, excuse me, machine learning is such a robust field, is because obviously the applications are immense and the tool is virtually the same every time. So that's an important feature, that even though we'll discuss many different physical systems in this class, the tools are going to be hauntingly familiar each time until finally you feel that they're almost second nature and you can apply them to almost any type of system. So one of the simplest machine learning algorithms is the so-called genomic type. And basically the idea is there that you represent the physical system as some kind of piece of DNA with a lot of little pieces and components. You run these pieces of DNA through the simulator and you get a performance metric that tells you how well they did. So if you're starting to think about an algorithm, you basically say the following: I'm going to generate a population of these possible system parameter choices. So it could be many vectors. Each choice is a vector, and the vector is n in length. So there are n components, and they could be things like, as I said, kinematics of arm 1, arm 2, arm 3 in a robot, laser intensity, you name it. An typical industrial problem will have several thousand of these parameters. We'll consider relatively complicated ones, but not on the order of thousands, probably on the orders of tens and 20s. That's what you can usually handle on a laptop. If you decide you wanted to go into more industrial type problems, of course, their parallel processing would be key. And we'll talk a little bit about that as the semester goes on. So the idea is we compare the simulated response for design I. So the I is a tag that tells me which design I'm looking at. I take the difference between that and the desired, I get a score. The lower the score, the better. And in fact, you really shouldn't refer to it as a score. You can refer to it as an error. So if the error is low, that's super. That's going to be a good gene. If the score is going to be high, meaning the error is big, that's bad. We take the winners in this gene pool. Let's suppose there are 100 of these. We take the top 20, we mate them together. So there's some type of a breeding process where you take a hybrid 1 and a hybrid 2, you create a child, you repeat this process over and over again, as we'll see in the details. And then basically, if we do this appropriately, eventually these kinds of genetic algorithms home in on exactly the right mix that is the best possible choice. Now, one nice thing about these algorithms are they give us many choices. There could be many possible combinations that deliver the best possible metric. And in that case, it's up to an engineer to figure out what she or he thinks is the most important in terms of, buildability, cost. And we'll include that in some of our later formulations. We'll put in cost as well. So it isn't just simply that simulated minus desired is the only metric. There could be something we add on to here, which is buildability and how much it's going to cost to actually make that thing that you're designing. And we can include that in many of our calculations. At any rate, so we generate a population, we check their performance, we breed the best ones, we throw away the ones that aren't doing well, we repeat it for the next generation by adding new ones into the system at random. So there's new genetic material coming into the mix. We add that to the existing parents and children, and we repeat the process over and over and over again. And if the process converges quickly, that's great. If the process takes a long time, we usually then apply all kinds of other tricks like gradient-based methods. And we'll talk a little bit more about that as we get closer. So let's look at an example. The typical example in the Bay Area is build me some kind of integrated circuit or large scale solar cell, something big, but at the same time with fine features. And that's usually what vexes most advanced manufacturing. We don't want just big things. We want big things with lots of little features, because the little features is where you can, make a lot of money. It could be a solar panel. For example, if you take a look at the magnifying glass and you really look at a solar panel, that thing has intricate weaving of circuits and NAND gates and all of the other stuff that is included in a high grade solar panel. That's not an easy thing to fabricate. In fact, it usually requires a great deal of care, which is what makes the panels relatively expensive. The raw material is not that expensive, but it's the features added that really make the cost shoot up. So if we were thinking about a 3-level type of material where we have some kind of a binder, but with specialized particles that give it some special property for layer 1, some specialized particles for layer 2, some specialized particles for layer 3, we have to figure out how to make this robot, number 1, manipulate all of these weird materials, make them into patterns at the mesoscale. So we're thinking microscale might be something on the order of microns. So this is finely ground up powders. Sometimes we call those nano inks or micro inks, where you have a fluid like acetone or some kind of binder with suspensions of little particles in it because you want it to be fluidized. Then you print it in some kind of crazy pattern, and then you basically build that over a large surface. So this is sometimes called a MMM problem. It is macro, meso, micro, and it's including all of the different features. So if we look at a simulation of one of these robots, this thing starts squirting out all of this ink. The ink is obviously on the micro scale. What's in the ink, of course, is on the, the ink itself is mesoscale. What's in the ink is micro, and then the pattern is, of course, the macro. So what we might want to print depends upon what application. Although in the Bay Area, the usual thing is something that has a specified elastic property, something that has a specified thermal property, something that has a specified electrical, magnetic, and optical property. Those are usually the big 5. Like if someone said, look, design for me some crazy weird circuit or some kind of an electrical gadget, almost always it's going to be some combination of these 5 properties, where 1 or 2 might be the most important, and a couple of the other ones are somewhat ancillary and not as important. It just depends upon the app. Now, the problem with all of this is that the materials are rare. I mean, if you want to make something that is of high value, very likely many people want to buy it, and if many people want to buy it, there's probably going to be a scarcity of it. That usually occurs in things like magnetic materials, neodymium materials that are, people are fighting about, where they're, I guess the ores are rare or hard to get at, or one country has a monopoly on them. Those are not easy things. So usually we try to do something clever by manipulating the microstructure, where we don't have to have a super special material, but if we use a composite material that has a little bit of the features of some of this rare material, but if we combine them, comes up with something even better, that is a value added plus. That means we can take off the shelf materials, powders, binders, microscale powders, electrical materials, and if we combine them right, they turn into a super material that has properties that are better than each of the individuals alone. And of course, we can tune them, and that is the key to classes in composite materials. So let's look at our first assignment. This will be your first assignment, your homework assignment. And let's take a look at what we're trying to motivate here. So let's take the typical example of a robot. It has 3 arms: big arm, little arm, small arm. Big arm is number 1, medium arm is 2, little arm is 3. It has an extruder that squirts out material. The robot is moving around in 3-dimensional space. The electrical fields that actually draw out the material, which is a pretty common thing in the Bay Area, are also a possible set of parameters. So we've got a lot of parameters going on here. We've got the angular motion of this arm, this arm, this arm. If it happened to also be telescopic, meaning that the arm could change, we can also have telescopic robots where arms are changing in length. That adds even, again, another feature. But the main point I want to make here is usually you don't care about the robot. You buy the robot and then you need to program it because nobody has the time and wherewithal to buy or create a new robot for every single application. So hopefully this robot that you buy, and of course there are lots of big vendors, Fanuc, KUKA, robot systems like that, you would buy those off the shelf and then try to program it cleverly to do something you want. And the something you want, there's pretty easy ones to motivate. Let's make a figure eight, for example, out of this weird material that's a combination. If I guess the parameters and just guess them out of the blue, it's very unlikely that I'm going to get exactly the pattern I want. I mean, the robot has so many degrees of freedom, especially with the materials. It may not necessarily make a wonderful figure eight. It might make something with some overlaps and loops. So clearly that is something that is going to be tough to guess. So just for the sake of argument, let's take the figure eight, the dashed lines. That's what I want, desired pattern. What I got was this kind of weird potato looking thing, the solid line. And so I take the difference between what I got and what I want, so I can give it a score. So for example, I could compute the path of this figure eight, and I'll say the difference between where this pattern is and this pattern is, I'm going to call that the difference, and I'll sum up in L2 the difference between what I got and what I have, and I'll give it a score. So for example, I might take the path that is been created by my simulation by guessing the parameters. I subtract away what I wanted, which was the figure eight. I divide by the total amount of the path of this thing just to give it a non-dimensional number. And basically what I have here is a percentage error between want and have. And all the parameters in the model are the kinematics of the robot, how it extrudes, etc. We'll get into those details shortly. The set of parameters are called the genetic string or the genome of the system. The idea is we need to figure out what the best combination of these genomes are to make this robot into a super robot that does exactly what we want, okay? So first we need a model, clearly. The model is basically going to be, in this case, I need to determine when a piece of material gets squirted out of here, I need to know where that piece of material is and what its velocity is, because after that, gravity is basically going to drag this thing and maybe the electric fields to a certain location where it splats, right? So the idea is as something gets squirted out here, like toothpaste, it gets guided to a certain location. And if I just got the parameters right, meaning I made the robot do exactly what I wanted, it moved around, it, jiggled the ink out, so forth, I would get a pretty good score, okay? So here's the model. The model is basically, I know the extruder position. So if I take a vector, R1, R2, and R3, I get to this location here, which is a piece of the material, the ink, okay? I add up those vectors and I can get the position of an extruded piece of material. And if I take their derivative, I get the velocity of the material. That's R dot. If I want to know the velocity of the material coming out of the dispenser, I have to add also the relative exit velocity, because obviously this thing is being squozen out with some speed. Now, it could be that it just simply pinches it off and is exactly the speed of the robot, then super. This term here would be zero. Otherwise, there's something that is the relative velocity coming out of the robot. The dynamics of this thing, which we'll spend all of next week on, which is essentially that we have F equals ma. So if I take a piece of material and I compute its velocity, I take its derivative, I multiply it by its mass, it should be equal to all the forces acting on that piece of material. So the piece of material has, if it's electrically charged, then we're going to consider a fancy case of electrically charged piece of material that comes out. It has an electric field that's around it. So that's something, you're the controller, you're controlling the electric field. It has also the magnetic field, and then it also has the velocity of the particle, and you multiply that by the charge. That's the so-called Lorentz force, which you may have seen as an undergraduate in a physics class. You have then the gravity, which is self-evident. That's obvious. Something is getting squirted out. Gravity takes over. And then finally, you also have drag, because there potentially is some kind of fluid in an ambient atmosphere that might be pushing or pulling these particles in the system as it's being deposited. That's very possible, because oftentimes in these kinds of processes, we have cooling fans. So there's definitely going to be some ambient draft that might potentially move things around if we're not careful. Okay. So at the same time, unfortunately for us, we also have the thermodynamics. So this problem is now going to become coupled. We not only have the dynamics of the object, but we now have also how hot it is. So theta will be the measure of the temperature in Kelvin. We have the derivative of the temperature multiplied times the heat capacity multiplied times the mass is equal to any conduction that is occurring. So if the particle hits the surface and makes contact with it, it's going to have some conduction. It will have convection because it's flying through the air, and potentially if there's some ambient atmosphere, it might cool or heat down this material. And then obviously we have radiation. So if this thing really gets heated up a lot, it might be glowing red. So it might radiate heat, or at the same time, the ambient atmosphere might be glowing red and actually imparts heat upon it. There are many manufacturing processes where the ambient atmosphere is actually much hotter than the particle that's being squirted out. And then finally, you have something called drag or ballistic drag, which is if you shoot these particles out fast, this is like a satellite coming into an atmosphere or a re-entry vehicle. And you've seen all these sci-fi movies where a satellite comes through and we hope that the astronauts are safe and everything's getting hot on this thing. Well, this is exactly like a satellite coming through an atmosphere. In many cases, these applications, people do what they call hydrodynamic printing, which means they shoot the crap out of this thing towards the target. So it could get hot simply by someone shooting out the particle. So that's what this term here actually gives us. So simultaneously with all that, we have this mixture of all of this gooey material where we have a binder shown here with small particles and big particles, which are what we call functionalizing particles. So this might be, for example, the binder might be a thermoplastic and the particles might be silver. That's a pretty common combination. And the reason is that the thermoplastic is easy to melt and is easy to mold. The silver is a pretty good conductor. And so we have something that then when it solidifies and hits the target, it's put into a form that we like. And at the same time, it's also electrically conductive. And of course, in the Bay Area, we love that because we love phones and all of the other charging gadgets and widgets and solar panels. This is what the combo is. So generally speaking, we have estimates for what the properties are for a piece of gooey material with multiple mixtures. And we're going to get to that later in the semester as well. And these are sometimes called mixture rules. They basically tell you that if you want to know, for example, the bulk modulus of the material, that's how squishy it is. Or if you want to know the shear modulus of material, that's how viscous it is. Or you want to know the conductivity, the thermal conductivity. If you want to know the electrical conductivity, permittivity, you name it, lots of properties, you can estimate what this mixture's property is by knowing the volume fraction of particle 2, these are the bigger particles, the properties of particle 2 labeled here with subscripts K2 and mu2, and the properties of K1 and mu1, which are the properties of the binder. If you know all of that stuff together, you can get an upper bound estimate of what the property is, the bulk modulus, based upon the constituents. Now, unfortunately, they're not exact. They only give you upper and lower bounds. So typically what people will do is they'll take the upper bound plus the lower bound and take their average and anoint that as the property that they're looking for. And you can do it for all of the various properties in the system. And these are tried and true. They're benchmarked and relatively, people have a lot of confidence in them. They use them all the time for these kinds of estimates, and we'll use them as the semester goes on as well. So let's get down to the final example, and then let's start talking about some details. So the idea is that when we have, let me go back, sorry about that. When we have the machine learning parameters, we have machine learning parameter, the kinematics of this arm, this arm, this arm, we better have a fast simulator. So our fast simulator has got to do something. It's got to do the following. It has to solve these two differential equations fast. So we've got to be able to discretize them quickly, numerically, and be able to do them and time step them forward in time. So as you might have read in chapter 2, we have a little bit of a review for you on time stepping schemes. One of the most common ones is to use what we call a forward Euler scheme. What we do is we take the velocity, we divide it into the velocity at time t plus delta t and time t. We divide by delta t, we get an estimate for the acceleration. We do the same thing for the position. We take r of t plus delta t minus r of t divided by delta t. That gives us the velocity. We stick both of those rascals into the differential equation, and we're able to get at any given moment in time the velocity and the position of any of those particles that just got squozen out of this robot. So the point is that every time this robot squirts out something, we got to keep track of it. So the more and more of these squirts we have, the more and more particles we have, which means this thing better be able to simulate this fast. Now, it gets complicated, of course, because not only do we have the positions and the velocities, we also have to know the thermal states, because we have to know how hot it is, whether it's melted, if it hits the target, is it going to splat, or is it going to sit there like a little clump of, clay? All of those things we have to know. So we have to know its velocity, its position, and its temperature at any given time for every one of the droplets. So as you'll see, and we'll teach you how to code this, in assignment number 1, if you do this properly with a forward Euler scheme, probably not with MATLAB, but MATLAB is good enough for assignments, and so is Python. But if you were to use some industrial strength, type of simulator, for example, C, this code runs in about a 30th of a second, as I said last time in class, which means that if I can do 30 of these entire runs, this whole entire simulation in a second, that means that if I multiply by how many seconds are in an hour, I get 108,000. So I can basically test a lot of different designs with this kind of a system. Now, the problem is even 108,000, while that may sound like an incredible number, there might be millions of parameter settings that are going to deliver potential possible candidates for a good robot setting. So even that is not going to be fast enough if I want to do this, in a couple of minutes. So this is where our genetic algorithm comes along. The basic idea is we take all those parameters in the system, we represent the kinematics of the arm, the extruder, the external electric and magnetic field. We put that into our simulator. What that means is we go into here, we stick those parameters into the model, and we run it. If it runs fast, we get an immediate gratification. We know exactly what the performance was of that thing, and we test the next one. And we go through this entire population. So, for example, let's suppose we have 100 designs in this gene pool. We test all 100, we rank them, and we decide, and this is something that you as the user or the code designer will do, you throw away, let's say 80, and you keep 20. What you do then after that is you basically take the top 20, you combine them appropriately. Kevin, can you turn off your mic? So basically what you do is you essentially take the designs, you rank them, you then throw away the ones that are losers, meaning they didn't do a very good job, and you keep combining them over and over until you optimize this response. And the response, of course, as we said, was we want to get that pattern right. So in summary, here's how it works. You take this design, you guess a parameter set, and the robot goes wild. It's not going to come even close to making that figure 8. So this was the very first guess at random, even though I know the parameter settings that I need for the figure 8 because I designed this model problem. This was the first guess. It goes wild. Like it squirts the ink up and down. I mean, it's going nuts. There's no way it's going to come up with the pattern. So what I did was I took 100 possible designs at random. I guessed them, and I plotted all of the different possibilities onto a chart. The chart is basically the following. It says, take the score, meaning the pattern I got and the pattern that I wanted right there, right? And I'm going to take that pattern and I'm basically going to give it a score of the difference between have, want divided by have. So it's a percentage error. The best possible design in the very first guess that I made was about 70%, or sorry, 80% in error. So it's just a little bit cut off there. The average of all of the population that was in there was about 80% in error. So everybody here was about equally as bad. These two plots here show that to be the case. Green is the average of the population. Red is the best possible performer. The difference between the best, which was about 71%, and the average was about 80% is not big. So I apply the algorithm again. I take the winners, throw away the losers. I rerun it again, and it knocked it down to about 58%. I then do it again, and it knocked it down to about 48%, and then it tanked for a while. It kept looking and looking and looking, and it found nothing. Then it found again another set of parameters, a big jump here at around generation number 25. And then it basically tanked for a while. Then at around generation 50, it found something a little bit better. And it did all of this thing in this tournament of champions of generations. It did this all in about 30 minutes. Now, the main point is that it zoomed in on all of the parameter sets that were able to deliver a 4% error, meaning that it was able to whittle down all of the parameters to get down to roughly 4% between what it got and what it desired without ever doing any physical, calculations, physical experiments. Now, at this point, this is where the intuition of the engineer comes in. The question is, which one of these designs are the best? So I've plotted the top six. The top six were, the first four were in the noise in terms of their differences. You'll notice it's 4% and a little bit of change, but the parameters are completely different. The kinematics of the first arm are minus 12.8, so that's radians per second. That was how fast it was spinning. The other next design was only 9.83. The other one was 8.97. They were 10. These are completely different. So are the kinematics of the second arm, the third arm, the extrusion velocity, the electrical and magnetic fields. The point is, some of these designs are cheaper to make, and some of these designs are more expensive to make. So at this point, the engineer has to come in and use, their intuition to basically figure out which one is the best choice. Okay. So in summary, that's our first model problem that we want to build towards. What we're going to do after that is we're going to start to delve deeply into the physics of exactly how do we estimate these kinds of properties, how we determine how heat and temperature and stress and strain affect materials, how lasers do these kinds of things, because that model that we just looked at, again, as nice as it is, it's a little bit, suboptimal in the sense that it's a little bit too much of a simplification. Materials aren't simply one big blob of stuff. They're mixtures of components, so we need to do a better job estimating that. When a material hits an interface, we need to know exactly what it does. I mean, does it splat? Does it sit there? That's all a function of continuum mechanics. How fast is the fluid velocity when it comes out of here? How does that affect what's happening in the material? All of those questions are things we need to take care of. So now let's start with details. So that's the motivation. Before I continue, are there any questions before we start to now get into some math? So that was, I hope, a good motivator. You should be in chapter 3. Hopefully you will have read it by today or tomorrow, but we're going to start to delve down deeply into exactly how does what I just showed you work. Any questions? All right, let's take a look at how this works. So here's the basic idea. Whenever we have some kind of an optimization problem, we're going to call what we want and what we have want minus have in an appropriate norm, so it's positive, divided by want. And that's a gross oversimplification of really what we're after here, but it gets the point here that if we have, for example, some kind of a cost function, this is what we call a cost function, right? And we have some kind of parameter that it depends upon. I'll call it lambda. Of course, there could be many of these, right? But I'm just going to show a single axis. And if I plotted pi as a function of lambda, it might look something like that, kind of squiggly, right? Now, if this thing was, if I wanted to figure out what the best one is, obviously that one looks like the one that has the lowest error, because again, this is error. That error here that's given here is basically given by when the gradient of pi is equal to 0, meaning if I know from basic calculus this is some function of lambda, clearly if I take the partial of pi with respect to lambda and set it equal to 0, I should get down to the bottom here. Now, the problem is going to be that there are many little wiggles. As you'll notice, there's something pathological about this function. If you notice, it's wiggling back and forth. I'll just exaggerate it. But that in real life is essentially what happens in most physical engineering designs. There's going to be what we call local minima, which means there's a minimum in this vicinity, but there's going to be also a global minimum, which is really what we want, which is the best possible choice in the whole design parameter space. Now, classical methods that were started with Newton, obviously Newton, that's Newton's method. Basically what they did is they figured out a method by which they said, you know what, I'm going to first assume this problem is a little bit simpler. I'm going to assume it's just a big bowl, okay? So I'm going to assume there are no wiggles, and I just want to get down to the bottom of one of these local minima, and I'm going to develop a method to do that. Chapter 3 starts out with exactly this premise. We're going to basically assume it's what we call convex. So what this means is convex means one minimum, okay? So we're from the get-go, we're assuming that we can get down to the bottom here, and that if we get down to the bottom, it is the quote unquote the bottom. So there is not a competing bottom. So in other words, something like this is not what we're after right now. We're not going to be able to get to both of the bottoms. We're just going to get down to here, okay, to one of them, right? So here's the basic idea. Let's look first at chapter 3 and kind of get the lay of the land, and then let's derive everything step by step. The idea is going to be that we're going to set up something like Newton's method that we know for a single variable. Newton's method, of course, is a root finding technique in its most primitive way, which is simply that whenever you have a function, you try to find the zero of a function. So what we are seeing here is, in fact, a classical Newton type approach to force something to be zero. Now, the problem is this does not imply that pi is equal to 0. Pi equals to 0 is a utopia, because that means I can find exactly the parameter sets that exactly give me what I desired. They may not necessarily occur. I may be able to get kind of close, but I may be only to drive this down to, as we saw in the other example, 4% error. In fact, I had 4% error was about the best we could do with that robot. So in other words, it is not always possible to get this to have equals exactly what you want, but you can get the closest possible. And the criteria for that is pretty clear. It's that the gradient is equal to 0. So this is our objective right now, is we want to force the gradient to equal to 0. Now we have a problem. If everything was just 1D, this would be a pretty simple thing. But unfortunately, this thing is multi-D, meaning there are many possible parameters. There's a lambda 1, a lambda 2, a lambda 3, a lambda 4, a lambda 5, etc. And I can't draw them obviously in hyperspace, because clearly I can only get away with possibly at most, I could probably draw something that is two-dimensional, lambda 1, lambda 2, and pi, and make some kind of a surface, but that's about as far as it goes. We have to think in the abstract. So in the abstract, we're going to have many parameters. So we're going to call the design parameters here lambda 1, lambda 2, lambda 3, all the way to lambda n. These are the design parameters, and this is the design vector, okay? So that's the basic idea here, is that we want to now figure out what the optimal choices are of these parameters, so that when we stick it into this function, we get as close as possible to want minus have divided by want to get to 0. Second best, of course, which is the only what we can assume, is that we want the gradient to be equal to 0. Okay, so what happens in chapter 3 is we go through those basic ideas. We understand a bit about Newton's method, but what we're going to find out is it has some fatal flaws. Number one, virtually nothing is going to be perfectly bowl-like. I mean, life would be too simple if it was that case. And number two, in many cases, when you look at a zoom of what's going on here, this function might have discontinuities where it might jump back and forth, and it might not be very smooth. So the problem is functions that have these abrupt jumps and things like this, it's going to be very difficult to take a gradient and a derivative, as we'll see, because to have derivatives, you need things to be continuous and smooth. And so if you try to take derivatives of things, for example, just to make it a little bit more extreme, imagine we had a function that looks like this. It's linear, and then it jumps up here and does this, right? Or does something like that. Let's even better. Let's draw it like this. There's a function like this, and then right at the top here, it does that. So the first question is, what is the derivative at this location? Well, from this side, it's some given slope, and from this side is some given slope, but right there at the intersection where this function meets, there's no definition of the derivative. Now, in 1D, we might be able to reason out, well, let's just be careful and watch out for those zones. The problem is in multi-dimensions, if we start to think about what that looks like, these functions are going to be, of course, in 3D, they're going to have little walls that might have a function that breaks off and does this, and then it might have another wall over here, and the function might break off like this. And so there'll be discontinuities in all of these regions here and here. That's dictated by the physics. So for example, where would this kind of an event occur? In robots, it's all the time when the robot jerks around. So if you've all seen manufacturing plants, like you look at a video of any kind of car manufacturing plant, and you watch an arm go this, that, and then moves very quickly and abruptly. All those kinds of sudden changes in their positions, accelerations, and velocities are going to lead to functions with a bunch of discontinuities in them. So if you have something that inherently has jerky type of physics, it's going to come back to haunt you later when you start to do this kind of optimization. So that's a reality that will occur in many of these kinds of approaches. So as I said, roughly around 1974, this guy named John Holland came up with a method, and he said, you know, I don't want to take derivatives because my functions are never smooth. I want this thing to run in parallel. So parallel processing was just starting along. There was this guy, Seymour Cray of Cray Machines, had started to create very fast parallel machines. So that was an important aspect of a lot of what people were thinking about in computing. So he came up with a method that comes up with this kind of gene thing that we talked about in our design. And so what I'm going to do in the next day or two, this lecture and the one on Tuesday, is we'll talk about how this method works. And then we're going to basically come back and home in on the robot. So homing in on the robot means chapter 4 would be a good idea to read before next week, because then what we're going to do is we're going to apply this to exactly the problem you've already seen, and that will be your first assignment. So Brian will send that out shortly so you can get a chance to look at it. So let's start now with doing the details of exactly this thing. But before I do that, are there any questions? Don't be shy. We have kind of a flipped classroom approach here. I give you a lot of stuff to read. Therefore, we have more time to yak in class. So are there any questions? Now's the time to start getting into the habit of asking questions in class. Daniel, you don't have a question? You always have questions.
Well, a lot of this is familiar from 280A, so I don't have
any questions
any
yet?
questions at the moment.
All right. Anybody else? Okay, well, let's get started with this thing. So packet number 3. So packet number 3, basically we have a design vector lambda. It has all these components, lambda 1 all the way through lambda n. Okay, So there are n design parameters. And the idea is my evaluation of how well these parameters do in the physical system, which I won't talk about yet. We already know kind of what it is because our first example is going to be the robot. So we got a pretty good inkling of what this pi thing is. Pi is basically robot performance. Now, later we're going to do robot, laser, material, solar farm, you name it. It'll be a different thing. But right now you should be keeping in the back of your mind what I really mean by performance is I want that robot to do something that I had specified, like make the pattern. So this is going to be equal to want, have, divided by want. Now, it's important to notice here absolute values here. So the absolute values indicate and ensure that this thing is always greater than 0 and is only equal to 0 and 1 in one case alone, when exactly have equals want. Want in the numerator and the denominator is just there to divide it so that it's a non-dimensional number. Sometimes that's an easy thing to motivate. Some other applications that may not be the easiest thing to do. But for this one, it's pretty simple. We already know that we're thinking about the robot making this figure 8 or some other kind of a pattern, and therefore want is really the figure 8 I want, and have might be, for example, a cuckoo pattern that the robot wasn't able to do. So the difference between the red and the black thing is my error, okay? So that's the idea behind this. All right, so first possible approach. The idea will be, I want to figure out what the minimum of pi is over all of the possible sets of parameters lambda. So my approach using classical calculus is to basically take the gradient of pi with respect to lambda and set it equal to 0. Now we have to be careful because now this is a gradient with respect to a vector. Pi is a scalar. Lambda is a vector. This compact notation really means that if I take the gradient of pi with respect to that vector, that's a vector called partial of pi with respect to lambda 1, partial of pi with respect to lambda 2, all the way down to partial of pi with respect to lambda n. And I'm going to set that equal to the 0 vector. That means 0 all the way down to 0 here. Okay, so this is a very complicated thing in disguise. This is not just a single number. It's going to be a set of many different numbers that I have to force. So really what I'm saying is I am forcing the tangent with respect, the partial derivative with respect to lambda 1 to be equal to 0, the tangent with respect to lambda 2 equal to 0, tangent of lambda 3 at lambda n equal to 0. So if you're thinking about the simplest case, this thing is just a bowl, paraboloid in space. This would be if this was lambda 1 and this was lambda 2 and this was pi. We're down here at the bottom where partial of pi with respect to lambda 1 is equal to the partial of pi with respect to lambda 2, which is both equal to 0. Okay, that is what we want. We just now want this, we're somewhat greedy. We want it for all of the functions, n. So n parameters. So in hyperspace, that usually requires us to do something that is usually akin to Newton's method. So Newton's method basically starts out for multi-dimensions in the following way. We take the gradient of pi, which is what we want to force to equal to 0. So that is our objective. Okay. And what I'm going to do is I'm going to expand that in a Taylor series. So I'm going to take the gradient of pi, and I'm going to put in here, for example, a guessed value of lambda, and I'm going to make a guess of it. So bear with me. I'm just writing this out here. I'm going to guess the value. My very first guess, I equals to 0. I'm going to guess the parameter states, and I'm going to expand around it by taking the gradient of the gradient of pi. So that's a new and complicated thing. That's the gradient of pi, right? And this gradient of the gradient of pi, I'm going to evaluate that at lambda I. So at my guess, again, same guess there. And I'm going to multiply it by, and I have to put that on a separate line, the vector lambda I plus 1 minus lambda I, right? And then I'm going to keep expanding the Taylor series, but because I'm a lazy person, I'm going to drop them. So the higher order terms, hot terms, bye-bye. I'm just keeping the linear stuff. So I've done a little local Taylor series expansion where I have expanded about the state here, lambda I, and I'm going to force this whole thing to equal 0. That's my objective. So really what I'm saying is I want my next guess to be equal to 0 to produce a 0 gradient. And I'm going to first check what it already did and add on this little piece here and try to force it to be equal to 0. Now, this gives me an equation. If I rearrange this thing, really what it looks like is gradient of pi evaluated at lambda I, now multiplied times lambda I plus 1 minus lambda I equals to minus the gradient of pi evaluated also at lambda I. This thing, to have shorthand notation, we're going to call it H. So it's a matrix, as we'll see in a moment, and we're going to call this thing G for gradient. So what this looks like when we look at it, it looks like H, matrix, multiplied, and where every term there is evaluated at lambda I, multiplied times the vector lambda I plus 1 minus lambda I equals to minus the gradient G, also evaluated at lambda I. So first question for you guys, what's unknown here? What do I want?
The successive term is unknown.
So the lambda I plus 1 is not known. So this is my objective. I want this thing because this will tell me what my next new guess is, and it should be better because I'm trying to force it towards the location of gradient of pi equal to 0. So I need to solve for this thing. So solving for this thing means I've got to invert this matrix, right? And what does that matrix look like? It's right over here. So it's basically this guy here that is all of this stuff. It's the matrix of all the possible second derivatives of pi. We'll come back to that in a moment. But this is an n by n matrix, n by n. This is an n by 1 vector, and this is an n by 1 vector, okay? So to invert it, I get lambda I plus 1 minus lambda I equals to minus inverse of this H matrix, the so-called Hessian. So I may have not said what it was. It's the Hessian, multiplied times the gradient vector. Now, I got to do some work to be able to get this thing, right? So if this thing is a lot of parameters, right, inverting the Hessian might not be the easiest thing to do. In other words, I have to basically take this thing and invert the matrix. We're going to see a lot of things that's going to make this thing a daunting task in a moment. But basically, we have this matrix system. We've inverted it, multiplied by G. And if you're thinking about MATLAB, this would just be G backslash H, right? We're just plain old matrix. Now I can solve for my lambda I plus 1, because lambda I plus 1 is just the previous value, lambda I brought that to the other side of the equation, minus the inverse of the Hessian evaluated at lambda I times the vector G, which is also evaluated at lambda I. So everything over here is known. This is known. H is known because I'm simply going to evaluate at all the lambda i's, and G is known because I'm evaluating it also at the lambda i's. What's not known is this, but this is what I want. So this basically gives me my desired new vector of parameters. Okay, so the idea here is I'm going to do this over and over again now. I'm going to basically take my guess of whatever I put here. I'm going to manufacture this H. I'm going to manufacture this G. I'm going to multiply them. I'm going to put it and get a new one. Then I'm going to put that back in here. And I'm going to do this over and over again in an iterative cycle, right? So the idea is that if I keep doing this over and over again, eventually I get down to gradient of pi with respect to lambda is equal to 0. Now, there are a number of things here that I've glossed over. Number one, this is, of course, a vector value thing, so this is really the gradient of pi. So again, it's many of these equations that are equal to the 0 vector, so we shouldn't think of it as one dimension. But there are a couple of other things that are, annoying about this method. Number one, we have to compute partial of pi with respect to lambda I, number one, partial of pi with respect to lambda 2, partial of pi with respect to lambda 3, and so forth. And that might be not an easy thing to compute. So if this is a complicated system, I have to figure out a way to actually compute a derivative of things. Now, here's where you have to be somewhat clever about it. So let's suppose we had our model. Deep inside of this black box is a robot doing something, right? It's squirting out stuff and it's making a pattern. I put in my parameters, all of my lambda i's. I get out the performance, which is pi evaluated at lambda I. Okay. Now, the question I have is, when I do this, how do I get a derivative? So this is some complicated monster simulation with all kinds of stuff. I ran it. So for example, let's suppose it was a finite element code or a robot code, and it went through all the crazy motions. The robot squirreled around, made all kinds of junk, and came back. But how do I get something like this term, partial of pi with respect to lambda? How do I get that? Well, suppose I ran the code twice. So let's suppose I take the code and I ran it first with this set of parameters. But now let's suppose I take the code again. I'm assuming that I have a pretty good code and it's been encoded properly. Let me take lambda I and I'll perturb it by a little lambda I. Okay, so I'm going to perturb everything and I'm going to perturb the thing. And now what happens when it comes out of here? It's going to give me the evaluation of pi evaluated at lambda plus delta lambda I, right? What happens if I take the difference between my first run? So I run my computer code, I get a response. I run my computer code, I get another response. What happens if I take the difference between this and this? What do I get? Well, lambda I plus delta lambda I minus pi lambda I, right? If I divided it by the amount that I perturbed it, delta lambda I, this actually is approximately equal to the partial of pi with respect to lambda I for the first component. Let's say it's the first component. So we have to be careful here. That's a partial derivative. And let me be a little bit less sloppy. This is the first component. This is the first component. Just a second. Okay, so what this yields is if I run my computer twice, so
The second time I ran it with the perturbed value and the robot did another crazy thing. And then this time it did this crazy thing. But if I take the difference between the first run and the second run, and I divide it by how much the difference was that I perturbed it, I get an evaluation of lambda, its partial derivative. This is a very important thing to understand when you're writing computer codes. This is sometimes called automatic differentiation. People attempt to make a code compute its derivative. So what will happen is people will take codes and automatically perturb them by all of the parameters in the system and attempt by doing these small perturbations to get an approximation of the derivative. Now, that's important because as you see here on the left, we need to compute that for parameter number 1, parameter number 2, all the way down to parameter number n. In other words, our vector of all of these parameters in here has many components. So I have to basically come along, run the code, run it with parameter perturbations, do this over and over again, et cetera, et cetera, et cetera, to construct the approximation of G, which is the partial of pi with respect to lambda 1, partial of pi with respect to lambda 2, all the way down to partial of pi with respect to lambda n. How many times do I have to do that? How many computer runs do I have to make to compute this thing? Someone tell me.
It would be 2n.
Close, but I can do some cheap recycling. The very first state here is the same one for all of them because it's always going to be starting at the very first state. So in fact, you're close. It would be, I have to do it n times, but n times perturbed away from the very first state. So it's actually n plus 1. That's about as cheap as I can do it. Does everybody see that? Yes, thumbs up. Okay. That's the easy one. I ran my code now n plus 1 times. So now the first thing to think about is, okay, I've constructed this derivative. If I have 1,000 parameters, n was 1,000, that means I have to run this 1,001 times for the very first derivative to get the vector. How many times do I have to run it to get this monster? Well, now let's focus on the Hessian. So we have our equation. It's H inverse G minus plus lambda I equals lambda I plus 1. So this one we already know. This one we just computed. What does this one look like? Well, let's look at what the Hessian looks like in all of its glory. It is an n by n matrix. It's the partial of pi with respect to lambda 1, second derivative, partial of pi with respect to lambda 1, lambda 2, mixed derivative, all the way down to partial of pi with respect to lambda 1, partial of pi with respect to lambda n. How many derivatives are here? There are n. How many derivatives are here going down? There are n. There are n by n times you have to compute the second derivative. In other words, the number of derivatives you have here, how many times do I have to do that operation for different parameters? So if I have 1,000 parameters in my model, how many derivatives do I have to compute?
1,000,000.
That's right. That's the bad news. But they're not just single derivatives, they're second derivatives. So now we got a problem. We got to take a second derivative and we've got to do it 1,000,000 times, just at that one step, right? So we're going to do many of these Newton steps. If we remember, how does Newton's method work? It has this cycle, right? It's going to basically cycle around here. And every single time we do one iteration, we have to compute all the crap here for the Hessian and the gradient. So 1,000,000 times here, 1,000 times there. So That's a lot of calculating to go through. I mean, Newton's method, at first it seems so simple, but it runs into all kinds of problems. It's kind of pricey. So let's look, however, at these derivatives. They're not as easy to get either. So how did we compute the gradient components? Well, we ran the code once, then we ran it again. We took the difference between them and we computed the gradients components. How do we do second derivatives? Well, second derivatives are not that simple either. So I gave you a little bit of some, background on how to do numerical derivatives here in the notes, but let's take a look at what they look like. A typical second derivative looks like this. If I needed to compute, excuse me, second derivative of pi with respect to, let's say, lambda 1, this is approximately equal to pi evaluated at lambda 1 plus delta lambda 1 minus 2 pi of evaluated at lambda 1 plus pi evaluated at lambda 1 minus delta lambda 1 divided by delta lambda 1 squared. That's sometimes called the central difference approximation of a derivative. So what I show you here is how you derive that approximation. It's again by doing Taylor series expansions, and you can actually get that whole thing here, right here. Now the problem is you don't just need the second derivatives with respect to each of the primary variables. You also need to compute, terms like partial of pi with respect to lambda 1 with respect to lambda 2, because you need all the mixed derivatives. So this Hessian, it's got all kinds of junk here. It's got the second derivatives off diagonal. It's got the ones on the diagonal. So how many times do I have to run the code to get this? Well, I have here n squared. So I've got n of these squared. And how much do I need to do to get each derivative? Well, I've got to run it here. I got to run it here. I got to run it here. I guess it's 3 times, right? Because every time I do one of these things, I got to do 3 runs. So one thing you can do, of course, you can recycle things. You can say, wait a minute, but I already computed this thing to get the gradient. Okay, that's true. If you're smart, you could bank it. You could save a little bit there. It's in the noise, but you could bank it and you could save a little bit. You might say, well, wait a minute, I've also computed a lot of these for the derivatives in the gradient. That's true too. You might have computed some of these. So if you're smart, you can do a lot of recycling of what you had to compute for the gradient to get the Hessian. But still, at the end of the day, it's a nasty number of terms you have to compute. It's on the order of n squared. There's just no way to get around that. So the problem is that this Newton's method, as simple as it is, and it's a pretty simple algorithm, right? You basically do the following. You have your scheme here. The scheme is basically that you take the Hessian, you take its inverse, you multiply times its gradient for a guessed value of lambda I, right? So you guess lambda I, you plug it into here, you plug it into here, you do some off-grid numerical calculations to get these G's and H's. But once you get it, you get your increment of your delta lambda, and you keep doing this thing over and over again. That is the classical Newton approach. Now, there are a couple of things that even notwithstanding all of the mess that you have to go through to form the Hessian, to form the gradient, there's a couple of things that are stinkers here. The first stinker is that you need to compute terms like partial of pi with respect to lambda and partial of pi with respect to lambda second derivative. So basically, you have terms that look like this. So help me out here. Let's suppose my function looks like this. What would happen if I tried to compute this term right there? Well, that's an inflection point, and the inflection point is going to force this thing to go to 0. It's going to transition from convex to concave. So let me try to draw my fingers right here. It's going to be a squiggly kind of a squiggle line here. So we know that there's going to be trouble right in that location. So number one, if our function has any wiggles, this thing is going to go nuts. And goes nuts means that all the terms here are going to start to go to zero on the diagonal. Now, why is that important? In other words, what happens? Let's look at a one-dimensional example to make it simpler to visualize. That's what it is in 1D, Newton's method. This is the dividing by the Hessian. This is the gradient. This is the vector. But since it's a scalar, I can actually directly just simply divide by it. And that makes it simpler to see. What happens if the second derivative of pi goes to zero?
Undefined.
It's going to explode, right? The algorithm is going to go nuts because the thing in the denominator goes to zero. So that's the first thing. Let's put here the list of flaws. Second derivative may go through zero. Now, the reason for that is when you have a function with any kind of wiggles, when it starts to change its curvature, the change in curvature means Hessian goes to zero. That's not good. Okay. Number two, what happens if the function is not smooth? So let's suppose it's a jerky function that looks like this. That could happen, right? Something messy. What happens at all these locations here? How do I compute the second derivative? In fact, how do I compute the first derivative? Well, at each one of these locations, the function looks like this. It's undefined. From this direction, it looks like the derivative is this. From this direction, it looks like the derivative is this. So if it's not smooth, let's write down the other flaw. Non-smooth. Trouble. So there's two things that doom Newton's method is second derivatives may go to zero. So that means that it's non-convex, meaning that there's not a single minimum. Number two, the functions are typically going to be non-smooth and you can't even take the derivatives. Okay, so while Newton's method has all kinds of wonderful utilities, they're mainly of academic interest, and it is a method that is going to be very difficult to apply in practice. So when you start to read chapter 3, go through the basics of the derivation of this. It shows you some of the numerical techniques by which to compute these derivatives. But I think we've sufficiently motivated that we better find something that's a little bit more robust, and that's where machine learning comes in. So on Tuesday, we will take this machine learning algorithm that you've already seen once before, this genomic thing, and we will derive it and understand the basic motivation for it. So if you're looking in the packet where this is described in depth, and this is what we'll do next time, is basically we're going to start here and we're going to attempt to figure out why would we need such a method for crazy functions that look like that, and why does it work? I think that's the most important thing, because if it didn't work, and it was a method that looked nice but didn't yield anything, then it would have died a very quick death in the world of numerical analysis. But this thing has really stood the test of time. It's out there everywhere. So if you want to learn more about genetic algorithms, of course, you can go into the literature. There's a lot, Wikipedia, it's all over the place. But there are journals that are associated with this. They're called journals of evolutionary computing, because they use this kind of evolution of a function to be able to optimize it. So I'll stop here, but what I would like for you to do is please read packet number 3, packet number 4 on robots. So we'll apply this genetic algorithm to a robot type problem. Okay, so we'll apply it so we can get a tangible feel for this. And that will be your first assignment to get sort of a feel of exactly how this works on a reasonably complex problem. So are there any questions before we sign off today?
I had a couple questions, but there's also a question in chat.
Oh, okay, let's see what the chat says. Somehow I lost the chat. Is the chat gone? Well, I'm not seeing it. It's not appearing. Could someone just, you can, oh, there it is. Sorry, behind us. Is the first line right on the right notebook saying that the first derivative is g? So on the first line on the right notebook, okay, the right notebook here, why don't you come online, Daniel, and tell me where you're looking so I can look in the same spot.
Top right of the image of the stream. So the other notebook, Untitled Notebook 2.
Here,
Yeah, on the top right, that first derivative, is
yeah,
that,
that's g.
that's G. Okay, thank you.
That's g, and this is h.
Is that
1D, it looks just like your old friend Newton's method from undergraduate days, which is just simply your guessed value, the derivative, the second derivative, and you keep plowing along. When it's multidimensional, G becomes a vector and H becomes a matrix, and you can obviously you can't divide by the matrix, therefore you have to basically invert this entire matrix, which is what's shown here in the notes.
Okay, thank you.
Sure. Any other questions, Daniel or anybody else?
Yeah. So regarding the computational cost of calculating the Hessian,
Yes.
I'm not entirely sure when it comes to numerical derivatives, but are we able to apply the symmetry of the Hessian
Yes,
to
in fact,
calculating?
that's a very good point. The matrix here is actually symmetric if it's smooth. If the function is smooth, the partial of, let me write it here. That's a very, very good point. If the function is smooth, the partial of pi with respect to lambda 1 with respect to lambda 2 is actually equal to the partial of pi with respect to lambda 2 with respect to lambda 1. They're one and the same. But that's provided that the function is smooth enough that it's continuous. In other words, you come from this direction, and they meet at some location. If the derivative or if the function has some behavior that looks like this, where it's different because of a discontinuity, then the symmetry isn't there. But then again, also you wouldn't apply this method at that for those kinds of problems. So to answer your question, indeed, this is you compute the diagonals and you compute the upper triangle of this matrix. That's all you have to compute. And then you could argue that this term and this term are the same. So you save a bit there.
Okay.
That's why I said that the method itself, depending upon the tricks, is of order n squared, but the pre-multiplier might be a half if you're clever, or it could even be narrowed down even to lower than a half. But it's still going to scale with basically the number of parameters squared.
Okay. And then also, where are the recordings going to be posted on B courses? Is it going to be like under the media tab?
Excellent question that only Brian can answer.
I believe it will automatically be uploaded to the media gallery tab.
Okay. Thank you.
We forgot to record the very first lecture, so if you were hunting for it and can't find it, don't worry, it's not there. It should be in the media gallery. So the way we're doing is right after class, Brian is going to download it from his computer and then put it into B courses. Now, the important thing is that Zoom is changing a bunch of stuff. They no longer want people to record things in the cloud. So there's all kinds of glitches in it, but we're going to go with the safe way. It takes a little while because Brian has to first get it processed on his machine, but hopefully within usually hour of the class, it'll be posted unless Brian has to eat dinner. That's up to Brian.
I'll get it posted as fast as possible. So
There you go. That's dedication. Okay. Any other questions? Brian, do you have any announcements that you want to make in terms of the assignment? I think you said you were going to release it tomorrow night. Is that correct?
yep. So I'm planning on releasing it tomorrow at 7 o'clock. I'm also planning on releasing the office hour for those who missed at the very beginning. I'm planning on releasing my office hours and the time for the help sessions tomorrow at 7 p.m. So please, if you have not filled out the when to meet survey that I sent out in an announcement on B courses, please fill that out before tomorrow at 7 o'clock.
Okay, so one question in general for all of you on screen, is the sound okay? And are the graphics okay? Because I can do mid-course corrections pretty soon, but I'm getting some fingers up, thumbs up. Okay, I'll assume I'll just continue with this style during the semester. You'll get the notes on one side, right? And then I'll repeat more or less the highlights on this side. And therefore, you can have everything and you don't have to scribble like crazy. And then periodically, what I'll do is I'll include some of the high-end graphics when needed. We'll go back to the reader. Okay, so hopefully that won't be too obtrusive, but I think that's sort of where I found the sweet spot from last semester and finally getting the hang of this. That's what I'll do. So hopefully that's okay with all of you as well. So have a nice weekend. Try to do a little bit of reading. The class is a little bit slow in the beginning, but it'll ramp up at a pretty good clip. Probably by the end of next week, we'll go from application to application. So see you later. Be safe. Try to get vaccinated if you can. Bye-bye.
Tarek.
Yeah.